I'm Trey Grainger. I'm the Director of Engineering for Search and Recommendations at CareerBuilder. And today I'm going to be talking with you about leveraging Lucene and Solr as a knowledge graph and intent engine. For those of you who don't know CareerBuilder or are unfamiliar with me, I joined CareerBuilder in 2007 as a software engineer. Got my MBA in Management of Technology from Georgia Tech. Got my undergrad at Furman. I'm currently pursuing some master's level classes in machine learning and information retrieval at Stanford. And when I'm not working, some of you guys may know me as the co-author of Solr in Action with Tim Potter. And I'm also the founder of SillyAccess.com, a gluten-free search engine. And my team and I are often contributors to Apache Lucene and Solr. One thing I will say, for those of you who are in here, I've got a copy of Solr in Action up here. I'm going to give away to whoever sends out what I find to be the most interesting tweet about this talk. So if you want a free book, you'll get a signed copy of it. Say something funny. Or mean. You won't get a book, though. So the agenda for today is... very quickly, I'm going to give an introduction about CareerBuilder for those of you who are unfamiliar with us, and then I'm going to define the problem as it relates to us and what we're trying to accomplish with semantic search. And then I'm going to walk through the steps of how we've built an intent engine to be able to do semantic search with a few key areas I'll focus on, one being type ahead prediction, spelling correction, entity type and entity resolution, semantic query parsing, query augmentation, and then a knowledge graph which ties everything together, and then I'll conclude with some questions at the end. So really quickly, Solr is key to most of what we do at CareerBuilder. I would say 90% of our products leverage search, and the search we have at CareerBuilder is Solr. We power our job search off of it, our resume search capabilities, our autocomplete, job recommendations, resume recommendations. We do a lot of analytics. We've got market supply and demand. Searching for companies, compensation, social media search, and just, it goes on and on from there. And we do a lot, if some of you guys have seen me speak before about some of the analytics work we do a lot leveraging Solr to be able to take the supply of candidates in the marketplace and the demand for jobs in the marketplace and put those into Solr and leverage it as an analytics engine to really be able to drive some really cool products to help recruiters target where they're trying to find candidates and to help just have a better feel for compensation, how easy or hard it is to hire in the market. The platform at CareerBuilder is at a decent scale. We get about 100 million queries coming through the system a day across about 1.5 billion documents throughout the system. We power this on about a little over 500 search servers, and we have 30 engineers in our search group that either manage the infrastructure, manage our core search platform, or build out our specific search-based products like job search, candidate search for our B2B products to help recruiters. And we also have a relevancy and recommendations team that focuses heavily on our recommendation engine, which is based on Solr, and also the general relevancy and semantic search capabilities that we have. We've got about 50 different search experiences across our platform. We've got dozens of international websites that we power, and we also have many B2B products that are emerging to be best in market. So the problem today that I want to walk us through is very fundamental to search. You guys probably all see this problem. You may not think about it that often, but I want to take us one step beyond text searching. So the problem in our domain is a query like this: machine learning, research and development, Portland, Oregon, software engineer, and Hadoop Java. This is kind of a heinous query, but it's not unreasonable to expect that someone on CareerBuilder might run a search somewhat like this. And there's a couple of things that you might notice immediately if you think about how the search engine is going to parse this that would be a problem. So a traditional search engine, whether you're talking about Lucene, Solr, any open source alternative, any commercial alternative, with a few exceptions, are going to probably parse this approximately as the word machine and the word learning and the word research and the word development and Portland, or as a Boolean operator, and so or is that with software and engineer and Hadoop and Java. So you'll find a lot of documents that match your query, and you're very much counting on TF-IDF or BM25 or whatever your relevancy algorithm is to hopefully bring the best documents to the top. But it's pretty clear that the search engine misinterpreted the meaning that the user had. It didn't do a good job at understanding their intent. So the question is, what would be a better parsing of this? You and I look at the original query, and we parse it out mentally as something more like this. That's a phrase machine learning, and a phrase research and development, and Portland, Oregon is a phrase or is not a Boolean operator, and software, engineer, and Hadoop and Java. So if we could get the search engine, when it sees this query coming in, to behave more like this, we'd be well on our way to really understanding the intent of the user and being able to model that out to get the right, to meet the right information need. But beyond that, what if we could go a step further and not just understand exactly the text they search for as phrases, but be able to actually expand that out based upon really having a deep, intimate knowledge of our domain. So in this case, machine learning is still there. It gets a high boost because it's what the user searched for. But also we know that data scientists and data mining and artificial intelligence are related to machine learning as well. Research and development and R&D are synonymous and probably used interchangeably. Portland, Oregon, we recognize as a location and also throw in a geofilter in there to actually search a radius around Portland as opposed to just the text, et cetera. And that's not to say this is the best way to represent this query, but it's moving us in the direction of not just searching on text, but actually searching on the meaning of what the user intended. And to go beyond that, we don't really want to search on those as just phrases. We don't want to search on strings. We want to search on things. And so when I go one step further and I look at a query like senior Hadoop developer at Google, really what we need to know is that senior is a job level, Hadoop developer is a job title, Google's a company, and then if I look at strategy consultant, McKinsey, Harvard, MBA, same kind of thing. Strategy consultant's a job title, McKinsey's a company, and a Harvard MBA is a school and degree combination. So how do we do this? So what I'm going to talk through today is what we've been working on at CareerBuilder to try to solve this problem. And the title of the talk is Building a Knowledge Graph and Intent Engine. And in that context, the green boxes that you see on the screen are effectively what the user sees. That's the touch points you have with the end user. So the keyword search box up in the top left corner, the user obviously interacts with you there. We've got one more piece, which is a user feedback loop, where as we're modifying the query and doing things, we want to give what we think the user's intent is back to the user so that they can correct us if we're wrong. And finally, at the very end, you have search results coming out, which is where you've actually done the matching. But there's a bunch of pieces that I've injected in the middle here that I'm going to talk about throughout the course of this time. So one of those is this idea of type-ahead predictions. You guys know that as autocomplete. I'm going to show you guys an example, if I can get the demo working, of some things we've done to go beyond just basic traditional autocomplete. But effectively, type-ahead prediction is as the user is typing, you show them what they probably mean and allow them to select that and see what the results would look like. Semantic query parsing is akin to what I showed you a few minutes ago, where we take that long query that the user typed in and actually parse it out into the appropriate understanding of the phrases. Spelling correction, I don't really need to talk about that. You guys all know what that is. There's many different implementations of that you can leverage in Lucene and Solr. We've done things slightly differently, but I won't spend so much time on that one. And then there's entity and entity type resolution, query augmentation, and a knowledge graph, which ties everything together. And those are going to be most of what I spent my time talking about today. Once you've done all of that to understand the intent of the user, you obviously still have to turn around and execute a search against the search engine. And that's the bottom left-hand corner here. I'm going to mostly stay away from that today. There's actually a really good talk by Bloomberg right after this about learning to rank. I would encourage you to go to that if you want to hear more. The other thing I'll say, though, is that when you look at all these boxes, my initial thought for most of them is, hey, you can't do that with Solr. I have to build my own application layer on top. And to some degree, that's true, but everything I'm going to show you today is actually leveraging Solr to do the very things that we're trying to do here. So I'll show you how we're doing it and how you could do the same. So autocomplete, everybody knows, is in Solr. Spelling correction is there as well. But also for the semantic query parsing, we're doing that in Solr, albeit there's some custom code, but I'll walk you through what it does. Entity type resolution, also taking place in Solr. Query augmentation, and even the knowledge graph, which I'll talk about, is built on Apache Solr. So very quickly, type ahead predictions. If you guys can see this here, it's basic autocomplete with a few differences. So it'll show the top terms coming up from any search. It also breaks things out by job title, skill, company, related keyword, et cetera, and all those different categories. It can understand abbreviations, alternate forms, and misspellings. So if I type in manger, it's going to understand that I probably meant to type manager. If I type registered nurse, it's going to understand that I meant registered nurse. And it also, what we've implemented supports the full Boolean syntax and also allows for multi-term queries. So I'm going to see really quickly if I can, let's see if I can get the demo working. Okay. So the example I was talking about, manager. So if I type manger, notice that it's identifying that as manager as a capability I might want. Also, if I want to continue searching for other things, say I search for Java, and now I want C#, or Solr. So Apache Solr and or Lucene. So one interesting thing to note here, most of this is UI magic, not core to the search engine, but we're actually leveraging a couple of capabilities here. The semantic parsing I'm going to talk about in a few minutes is a key part of this, where as the query is going in, we're able to parse these pieces out. And just to show you an example, which I'll have a slide for in just a minute, if I well, I'll come back to that in a second. But the gist of it is, for semantic autocomplete, I can type in anything, whether it's misspelling an acronym, a synonym. If I type CTO, notice Chief Technology Officer is what comes up, not just the letter CTO. It's nuanced. It's basic autocomplete, but the nuances are there that there's something more powerful going on under the covers, and I'll talk a little bit about how that works in a bit. Spelling correction, I'm going to spend very little time on. I showed you an example a second ago where I typed manger. If I would have typed, like I said, a registered nurse, it would have identified it as well. I'm going to just refer you to the Solr spell check component. Go Google it, and you can figure out how to do spell check yourself. So I'm not going to spend as much time on that today, but ask me after if you've got some questions about how we're doing it. And so now getting into entity-driven search a little bit. This is where some of the domain-specific work comes into play for us. But really what we want to make sure that we do is when someone's typing a search for CPA, we understand that that's certified public accountant. If they type the word driver in, we don't just search for the text driver. We understand that driver could be something in the transportation industry, or it could be something in the software industry. And we have some likelihood based upon what we know about the user about which context we're going to pick. So we do disambiguation there. Also, for beyond just words that mean the same thing, we also have related terms. So RN is related to nursing and Bachelor of Science in Nursing. Hadoop is related to MapReduce, Hive, and Pig, but they're not the same thing. But we can leverage those relationships, like I showed you earlier, to be able to expand the query to be more meaningful, to better represent the intent of the user. So fundamental to the approach that we take for at least part of this is the idea of building a taxonomy of entities. This is not something you get for free out of the box. There's numerous ways to do it. You could use topic modeling. You could take documents and you could cluster them to find interesting phrases. You could run some statistical processes across your documents to identify statistically improbable phrases. Or you could buy a dictionary if your search need isn't domain specific. But fundamentally, for a lot of the system to work, you have to be able to identify words and phrases that your users are going to be searching for. And the strategy that we take is we just mine our query logs. So we've got millions of queries coming in over time. We look at which users ran which searches and what other searches that those users ran. And we can see what the top searches are, mine those out, and create a list of entities that represent the things most commonly searched in our domain. And if we do collaborative filtering within those searches, we can also find related terms and phrases associated with the original phrase without having to do, without hardly having to lift a finger because it's all crowdsourced. Now, not everybody has the benefit of having massive amounts of query logs, but if you do have them, it's a really, really easy way to get a list of common entities that can go into a taxonomy. We've got several research papers as well, which I'll link to, which you can read about how we're doing some of this. Entity type recognition is another thing this one's going to be a little bit hard to do with out-of-the-box Solr. We actually had to go implement our own classification capabilities for this. But the idea here in our domain is that we want to be able to identify if a keyword is a skill, a job title, a company name, a location, and various other kinds of entities within our domain. And whatever work you do here is probably going to be domain specific, so I'm not going to spend as much time on this. This isn't actually a requirement for a semantic search system to work. It just makes it that much better, because instead of just searching for the phrases you found, you can actually search on those phrases in the specific field associated with them. So if someone types Microsoft, I can search for Microsoft in the company field. If I search for Scala, then I can search for that in the skill field or the keyword field. But what you can do, and what I'm going to walk you through now, is some semantic query parsing. And so just to rehash the need here, we talked about the machine learning example earlier with Portland, Oregon, and how the query on the right doesn't necessarily represent the actual intent of the user. But in the job search domain, here's a few examples where it's particularly interesting to see how the search engine parses it out and what that does to the results. So for project manager, if that gets broken into just project and manager, then I'm very likely to find a job for anyone who's ever managed a heavy workload and has worked on a project. If I look for a building architect for building and architect, or software architect for software and architect, it's worth considering that a software architect is someone who designs and builds software, and a building architect uses software to design architecture. And so if I search for just the word building, if I search for building, architect, and software, I would actually get a commonly overlapping set of results, because while the search engine may do a good job at bringing the right results back, it's not really understanding the intent and is actually making a mess of things in a lot of cases. So it's really important that we get the phrases correct here. And so in this example, if I type in senior software engineer, Perl, Hadoop, big data, what our technology is able to do is actually parse that out into the individual terms and phrases that are intended. Let me see if I can actually, see if I can remember what that search was. There we go. See if I can get this to work. Prove that this works. There you go. So I've got senior software engineer, Hadoop, and like I showed you a few minutes ago, we're not just parsing out the phrases, but we're actually understanding what the terms are that are related to those phrases. So in this case, we've automatically expanded the query out to not just be the phrases you typed in, but to actually be able to automatically include other words and phrases that might be similar to the search that you typed in. And we're not always going to be right, but that's why we present the information back to the end user, so that they can correct us if we're wrong, and then we can take what they corrected in as a feedback loop to make the system even better. So one of the things that you can take away from this that you could implement yourself is this idea of a probabilistic query parser. So one of the things we've done, while we definitely mined the entities to be able to figure out common known terms and phrases, like Hadoop, for example, had all those related terms that we'd mined out of our query logs, we also built a probabilistic parser. And what this does is allows us to take in the query as it comes and to break it into all the possible bigrams and trigrams, and then to score those against a language model that can tell us the likelihood of each of those words and phrases appearing. And then when we combine that all together, we're able to say what the most likely parsing of the query is. Here's some just pseudocode over here that kind of demonstrates what we're doing. Basically, imagine just applying naive Bayes to the term frequencies and document frequencies that are in the Solr index. And so when I say we have a language model, I should also say our language model is just the Solr index. So when you pass documents into Solr and parse them out, into unigrams that go into a content field, we can actually leverage the positions of those unigrams in terms of how they occur together to do interesting bit set intersections to figure out what the co-occurrences are of terms together and separately. And so this is an example of a request handler that we've built into Solr that is taking in what I just showed you, senior Hadoop developer, Java, Ruby on Rails, Perl, and it's parsing it out, and then it's breaking it, you can see down here, into lots of different permutations. You'll see, for example, developer Java Ruby gets a very low score. That phrase basically doesn't ever appear. Developer Java never appears. Java Ruby never appears. Ruby on does, but Ruby on Rails is more likely to appear as a phrase. And so by calculating all these separately, when we combine them together, we're able to predict the most likely parsing of the query. And anecdotally, for short phrases, we tend to be about 98% accurate. And for long, complex Boolean queries, we tend to be about 92% accurate. So it's not perfect, but it gets really close. Another thing we do is, in addition to the probabilistic query parsing, we do basic entity extraction on the queries or documents that come in, and we're able to extract out the phrases that went into the taxonomy that I talked with you about earlier that we built from mining our query logs. So one of the things we leverage heavily is the Solr text tagger. Great project. We use it very heavily. Effectively, we build the taxonomy up front. We take all the terms and phrases in that taxonomy and feed them into the Solr text tagger, which leverages the finite state transducers inside of Lucene and Solr to be able to very rapidly do naive entity extraction, where any of the phrases that are in our taxonomy, if we pass a document at the Solr text tagger, in milliseconds, it can tell us all of the phrases that were found within that document. It doesn't do much beyond that, meaning there's no scores associated with those phrases. It's just kind of a naive tagger, but I'll show you later how we've been able to actually score all of the terms that come back to be able to tell which of them are important and which of them aren't. After we've done that, we also separately invoke our probabilistic parser, and we actually use the output from the entity extraction from the Solr text tagger along with the probabilistic parsing, and we merge the two together. And so, for example, let's say I had the phrase senior Hadoop developer, and it wasn't in my corpus and the it wasn't in my taxonomy, but the probabilistic parser said, yeah, hey, this probably is a phrase. We can actually allow one to override the other, so it gives us a kind of check and balance to make sure we're not completely dependent upon one system. And then after we've fully parsed things out, so this is an example of walking through the Solr text tagger where we pass in the query software engineer and Hadoop Java, pass it to the Solr text tagger, and then what we get out of that is the phrase software engineer, the phrase Hadoop, and the phrase Java, each with a start and end position within the query that went in, and then we can substitute in tokens into the query as opposed to just leaving it as it was. So we end up with software engineer as a phrase, and Hadoop as a phrase, and Java as a phrase. Once we've done that, say we got the word machine learning parsed out in that last step, then we have this rich ontology, basically, of known keyword phrases that are related, related job titles, related occupations, et cetera, that we're able to learn. So for every term, we know everything in our domain that it's related to, whether it's a job title, a company, or a skill or anything like that. The way we do that we get those relationships is by leveraging the knowledge graph, which I'll talk with you about in just a few minutes. And then ultimately, once we've taken the word machine learning, checked against our knowledge graph to be able to figure out what it's related to, we then have to turn around and turn that into an actual query to Solr. So this isn't what we actually send to Solr, but just as an example, we could take the original term and search for it, say, now I have to match at least 2 of these other phrases, and also any documents that fall within the job titles that this word is classified to, we're going to boost those up to the top to help get rid of the noise. I don't know if you can see that from back there, but so this is an example of hitting our semantic search API where I'm passing in the keyword Hadoop, and it's showing me that the top job titles associated with this are software engineer, Hadoop DevOps engineer, Java developer, et cetera. And the top related keywords are Hadoop developer, MapReduce, Hive, HBase, Pig, big data, et cetera. Similarly, everything I've talked about thus far has been related to queries, but we actually treat a document as just an extension of a query. It's a longer query. And by leveraging the Solr text tagger and leveraging our knowledge graph, we can actually go from a large full text document and distill it down to just the words and phrases that actually matter to us, which are things that we've seen before in our domain from our taxonomy. And then from there, we can actually score them with the knowledge graph. So you'll see in this case that this document was classified as, so this was a document for an accounts payable clerk. This is a job description, and we're able to identify that the job title is accounts payable clerk. The government occupational codes are bookkeeping, accounting, and auditing, billing, cost, and rate clerks, and some of the skills associated are bookkeeping, accounts payable, finance, and accounting. And what I mentioned earlier about leveraging the Solr text tagger, where it will identify all the words and phrases, but it doesn't actually tell you, which of them are important. It just identifies anything that's in the index. By leveraging our knowledge graph, we're able to actually take all of the things that we extracted out and score them relative to how interesting they are in terms of how well they describe the document. So for this big data engineer job here, job description goes after that. The top extracted keywords that came back from the Solr text tagger were rescored, and we see that the top most interesting keywords are data engineer, big data, Hadoop, Hive, MapReduce, and Pig. So you can tell that's doing a pretty good job at really understanding the meaning of the document, and then we can take that distilled meaning and turn around and run that as a query, basically doing content-based recommendations. So now to the knowledge graph. What is it? So we've just built the knowledge graph internally, and we're still trying to get a feel for what all we can do with it. It's built in Apache Solr, and it's effectively a data science toolkit that allows us to dynamically navigate and pivot through multiple levels of relationships between items in our domain. So just taking a step back for a second, all we're doing is we're taking millions of documents, putting them in a Solr index, and leveraging the statistics in that Solr index to be able to figure out what's related to what. So I'll walk through some examples in just a second, but it's basically a core similarity engine that we expose via an API. So we can take any skill or job title or company and ask, what are for example, for the job title Hadoop developer, what are the top skills associated with that? Think of it as doing faceting and then scoring the facet results that come back. And then, beyond that, if you want to pivot, you can say, what are the top job titles? And then pivot on that. What are the top skills associated with each of those top job titles? And you just can keep pivoting and slicing, dicing the data any way you want. So I'll show you an example in just a second. Actually, let me just go ahead and show you an example. This is going to be quite big. So this is our interface for our knowledge graph. What I'm doing is I'm passing in the query, just the text query of Hadoop. I could search on a title or a skill or whatever, because those are all fielded values in the index. And I'm saying search on the query of Hadoop, and then I want to compare keywords from our taxonomy, and I want to sort them by how related they are to my original query of Hadoop. And specifically, I'm going to pass in this list of values: Hadoop, registered nurse, Java, teacher, restaurant, .NET, farm, pig, bee, and hive. And then beyond that, I'm going to just get that list of keywords back, and then I'm also going to get the list of top job titles back. And for each of those job titles, I'm going to compare those with another pivoted level of skills. So let me send this to Solr. This is running on my USB thumb drive, so it's a little slow. But so what you see for my query for Hadoop, no surprise, Hadoop is the top most related thing to Hadoop. Hive is the next thing that comes up, followed by pig, Java, .NET, bee, farm, teacher, restaurant, registered nurse. So remember, the goal of this is to try to score things based on how similar they are to my original query. So from that list, Hadoop, Hive, Pig, those are all very related. Java is somewhat related to Hadoop. .NET's less related than Java, but still, positively correlated. B has no correlation whatsoever. And then farm, teacher, and restaurant are negatively correlated with my original query. So I can basically take any list of things and score them against anything else and tell how good it is at describing the intent of the user. And if I scroll down further, you see with the pivoting that the top job title that's most related to Hadoop is Hadoop DevOps Engineer, and then within that, the top skills are Apache Hadoop, Apache Hive, MapReduce, HBase, Big Data, NoSQL, Python, Java, it keeps going from there. Then if I go to Data Architect, I see a slightly different list, but fairly similar and overlapping. And so one of the points here I do want to just stress, if you're looking at this isn't just faceting. If I did faceting, I would see the top most commonly occurring things at the top. This is actually a measure of statistical relation. So I'm using the engine to either allow me to pass in a list of things to be scored, or if I don't pass in a list, it can auto-discover that list by doing faceting and then taking the faceting results and then scoring them based upon the actual relation. But what you see is you can come into this knowledge graph, you can pivot in any number of directions, and you can keep going from step to step, effectively from entity to entity in terms of those relations, all leveraging the inverted index and documents as the underlying connection mechanism that ties all those entities together. And so how this works, we are doing, this is something I talked about maybe 2 years back in a semantic search presentation, but effectively it's just a z-score. That's how we're measuring the statistical correlation. So in the example I showed you, Hive was the most positively correlated with Hadoop, and registered nurse was the most negatively correlated with Hadoop. But we're basically just passing that into the search engine, having it score, and then using whatever the top scores were. And so the more highly skewed a term is towards Hadoop, the more the higher the score is going to be, and vice versa if it's negatively skewed. And so for this knowledge graph, there's a lot of use cases, which we're just beginning to scratch the surface of. But it's basically a tool that allows us to discover relationships between anything. So I could ask it the question, if I want to become a data scientist and know Python, what library should I learn? By searching for data scientist, Python, and then looking at the top skills that come back. If my last job was a mid-level software engineer and my current job is an engineering lead, what are my most likely next roles? All I have to do is have, from a resume, 2 job titles ago, last job title, what's the next most likely job title that people progress into, and then break that down based upon how often they occur. Similarly, I can traverse arbitrarily deep and sort on pretty much anything. So what I showed you was a z-score. You could easily put naive Bayes or PMI or any other statistical measure in here and be able to dynamically look at those relationships. It's also useful for data cleansing. Anytime you have a dirty list of, not a list of dirty words, but a dirty list of words, and you need to figure out how to clean that data up, you can actually pass it in here and it will tell you, hey, out of these 10 things, this one thing is an oddball, throw it out. And then on the recommendations front, which my team focuses very heavily on, we can actually use this to figure out, to build a profile based upon search histories. So if someone comes in and searches for Java, and then they search for jQuery, and then they search for CSS, and then they search for JSP, when we look at the intersection and overlap of that in this knowledge graph, we're going to see a very different kind of profile than if someone searches for Java and then C++ and then assembly. And we're going to be able to see those intersections and overlaps and figure out what all the related things are to them and use that to build out a model of the user. It also is useful for crosswalking. So we can, if we have an ID field and we want to be able to do a free text search, but I can only search on IDs because it's tied to a database, I could run a free text search, see what IDs that search is most commonly associated with, and then turn around and run that search against the database to apply a layer on top. Similarly, if you had a location box and you could only search on state, but you really wanted people to be able to type in a city, you could actually allow them to type the city in, check the knowledge graph, see what state's most highly correlated with that city, and then run the search for that state. So there's all kinds of interesting things you could do there. And then finally, if you've got a list of taxonomies where you've got an old taxonomy and a new taxonomy, you could very easily use this to crosswalk to figure out what changed between versions and how highly correlated they are. So we've done a lot of work over the last year. Over the last 2 years, this is a list of publications between our search and data science teams that we've had. Most of them in some way are related to semantic search and data science and classification. Solr in Action was published last year as well, and we've spoken a lot about this. But this is an area we're focused very, very heavily on. You see the join our team thing up at the top right. We do have openings. If you're interested or know someone who might be, come talk with me. And then, so there's my little sales pitch. So the question now is what's next? So I showed you this graph. We talked about most of the things on here, but the one that we didn't talk about is down here in the bottom left-hand corner, which is actually taking all of this knowledge and being able to, now that we understand the intent of the user, how do we express that back to Solr as the actual query that's going to get us the best results? So I'll be honest, we haven't spent nearly as much time on this as we've spent really trying to understand the intent. This is our next area of investment. We're going to be looking very heavily at learning to rank, machine-based ranking. And like I said, there's a talk from the Bloomberg guys right after this one that you should go to if you're interested in this. But hopefully next time I come, if it's next year or whenever, I'll be able to talk a little bit about learning to rank, because that's the next thing we're going to be focused on. But that's pretty much my time. And I just wanted to end with this. You have the opportunity to interact with the user in the search box. You have the opportunity to show them search results. And most search apps, that's all you have. Basically, you go straight from the search box to Apache Solr and get search results. As users start getting more and more sophisticated with Solr, they'll start implementing autocomplete and spelling correction, all these kinds of things. But there's this whole realm of intent understanding that I think should be the next area for investigation for folks who are really interested in information retrieval and really trying to understand the user's intent. So a lot of people are doing work in this area. Today I just wanted to talk with you a little bit about what we've been doing at CareerBuilder. And none of this is open source yet. I'm sure we'll open source bits and pieces of it. But if you want to talk with me about how some of it works, feel free to come up afterwards. And on the relevancy front, I've given several presentations in the last couple of years about recommendations and personalized search and semantic search. They're really easy to find online if you want to go look at some of that. I didn't really get into, like I said, that bottom left box about actually building relevant queries. I didn't get into that today, but that's a whole another area worth many discussions. So last but not least, if you need to get in touch with me, Trey.Grainger@CareerBuilder.com. My Twitter handle is @Trey Grainger. You can go to my website and see any presentations or publications I've had. If you don't have a copy of Solr in Action, I highly recommend it. And if you want a free copy signed by me, put something interesting on Twitter, and probably tomorrow when I wake up, I'll see which tweet was the best and hunt you down. Do I have time for any questions, or are we done? Okay, we've got 2 minutes. Anybody questions? Yep. So the way we've built it, it's not distributed, meaning everything in the knowledge graph is optimized to be run really, really fast in real time as queries are coming in. So there's kind of two pieces to it. One is the taxonomy that I mentioned, and that's right now right around 100,000 entities. There's a little bit of noise in there, but it's pretty good all in all. We use that taxonomy and the Solr text tagger to tag documents, and then we turn around and feed those documents into another index, which is our corpus. That corpus, we tend to keep about 1 million documents in there. We keep just enough so that the statistics are representative of the larger population. Again, we don't want to be running every query against 100 million documents. So we keep it. Right now it's around 1 million, but we will fluctuate that based upon how it performs. No, it is best that it runs in a single shard, not distributed, because the whole purpose of this index is to be very quickly accessible, and it basically just serves as statistics to be able to find relations between things. So what we have is a separate index with our actual documents, and we use this as a knowledge base to figure out what queries to run against the main index of documents. Yep. Yep.
So to traverse the graph, do you store it denormalized to some extent, or you do kind of like joins through both?
Think of it as documents being the connections between, so if I've got a skill and I want to connect it to a job title, its relationship to that job title is entirely based upon the number of documents that overlap between the two. So the connections in the graph are actually the documents. Yep. So I'm out of time. If you guys want to chat about this more, I'll be around today and tomorrow. Hope you enjoyed it. Thanks.